Uh, Good morning, sir. Sancheti, sir. Hello.
Yeah, good morning.
Professor, can you hear me?
Yes, I can hear you.
Can you hear me?
Yes, I can hear you. Can you hear me?
Hello.
Good morning. Can you hear me?
Yes, sir.
Okay. Thank you.
Okay. Okay. Very good morning to everyone. So let's start the third day session of the workshop on mathematics for machine learning. So today with us we have an eminent speaker, Dr. Sancheti. So he's a chief operating officer at Algo Vision Technologies Private Limited. He has built embedded software groups at Algo, Motorola, Philips, and Insilica. Dr. Nirmal also runs Sankalan, a training organization with a focus on productivity improvement through building concepts. So Nirmal's training interests are in the areas of efficient and maintainable programming, data mining, and algorithms. So he has conducted training programs in the areas of data structures and algorithms, design and analysis of algorithms, signals and systems, digital signal processing, data mining, machine learning, linear algebra, effective programming, and developing quality software at Motorola, Philips, Samsung, Adobe, uh, Conexant, IIT Bangalore, BRITS Pilani, IT Kanpur. So I wholeheartedly invite Dr. Professor Nirmal to speak with us for this session. Sir, it's your turn to take it over the session. So you can start presenting.
I'll share my presentation. Just see if you can see it. Let me know. Can you see my presentation?
Easy.
Yeah, and you can see it moving also, right? I'm just changing slide. You can see the change of slide? Okay, let me see. Can you see it moving now? Okay, thank you. So let's start. Good morning, everyone. My name is Nirmal, and I work for a company called Olgo Vision. We are into video analytics, mainly for security applications. So let me start this talk, and I'll be talking today about linear regression, which is a very, very important topic in statistics. And probably we can say, as far as our machine learning is concerned, this could be one of the beginning topics. So, what I will do is I'll introduce the problem of regression. I will just see how we solve it for single variable, how do we solve it for multiple variables. Then we will introduce the concept of overfitting and underfitting, and then we'll see how do we overcome overfitting, and we'll see a very important analysis in terms of bias variance decomposition. And so please feel free to ask questions anytime during the talk if you have. Uh, is my voice clear enough? Okay, thank you. So, in reality, we have lot of examples of input and then corresponding outputs. For example, let's say I have house described by number of bedrooms and total area, and then I want to figure out what's the house price. That's the output. I have a lot of, let's say, another example could be I have a lot of company information. I have sales, margin, debt, etc. of the company, and then I want to predict the stock price. So, what do you want to do? Our aim is to fit a function f to the data we have, and we'll call these data as features. And once we so basically you have some set of data already where you know both the input and output. Why do you want to create f then? You want to create f so that what you can do is if you have some other input for which you don't know the output, then you can predict the output. And if the f is linear, then we call it linear regression. So right now, today our focus will be mainly on linear regression. So applications could be variety of applications like stock price prediction. We do weather forecasting. Can be used for interpolation. I mean, in engineering applications, many times we want to interpolate. We have different values given, but somewhere in between we want some values. We can use it for interpolation. We can use it for extrapolation as well. We can use it for business forecast, etc., etc. There are innumerable applications one can think of. So let's start with a very, very simple thing, and just say we want to do linear regression in one dimension. What does it mean? It means that I have been given some set of inputs x and corresponding output y, and both x and y are one dimension. So x is simply a number. So I have been given xi, yi pairs. Some n inputs are given, and I do know the relationship between them. So our aim is to find a function f which is relating x to y. That's our simple aim. Now we assume linear relationship. That means we can say y is equal to ax plus b, or we can also say y equal to ax. If we can choose the ax plus b is more general one, but for the time being, I'll start with y equal to ax. Now, in this equation, if I look at y equal to ax, the variables are not y and x. Variable is actually a. Because I don't know a, I've chosen a linear relationship, let's say y equal to ax, and I want to fit that y equal to ax to the data I have. So for a particular, A, it will fit the data well. Now, sometimes I need to choose AX plus B, and that will fit the data well. This is I am talking to you only about one dimensional X, but we could have many more features than just one feature, and we will talk about it later. So the examples could be, let's say I have been given some centimeters and inch data, just to give a very very easy example to see how it works, and or we have been given centigrade and Fahrenheit table, and we need to figure out, and let's say nobody told us how to convert centimeter to inch or how to convert centigrade to Fahrenheit. So these are not these are just toy examples, just to cooked up to show the methodology. And in real life, you will have a lot. Let's say you are given a lot of data in terms of you know. Features of when we're talking about company information. Let's say you have been given lots of years of years and years of data of stock, the company performance in terms of its financials, income, profit, the expenditure, and so on and so forth. And there are other global parameters given, like you have the inflation index, and there are lots of those things can be given, and then you are supposed to, and you have been also given the stock price of that stock, and you need to predict the stock price in future. So that kind of thing will probably be a more realistic example of regression than this one, but this is just to illustrate the methodology. Okay, so first thing, let's say I just given the inch to centimeter. If you look at the left side, I look at data. Then on the right side, I've given some centigrade to Fahrenheit table. So this is just it's a good idea always to first try to visualize the data you are going to deal with. So that's the our given data. So what I want to do now is I want to look at this data set, and for one dimension, so for only just y equal to ax, I want to fit the inch to centimeter kind of thing. So and two. So aim is to and if you look at the Fahrenheit to centigrade, we realize that at 0 degrees centigrade itself there is some value. So if I do y equal to ax, it's never going to match, because if x is 0, y is always going to be 0. So maybe ax plus b is a better fit for the second data set. So that's why it's very very important to look at the data and realize what we want, right? Okay. Now, so aim is to, let's say we know the form y equal to ax plus b, and I have some data of xy pair given, and we want to find the pair AB such that we can predict y for any x. Now, and how do we know how well it is doing? So minimally, it should perform well on the given data, and that, if time permits, we'll get into that. That may not be good enough, but at least that's a minimum I should expect, that whatever data has been given to me, at least it performs well enough on that. So how to ensure? So what I do is, for a given pair xi, yi, let's say what is the error. So error will be, if I use this equation here to predict, then if this is the equation I use to predict, what I see is my prediction would have been at a of xi plus b. So that's my prediction, and actual value also was given to me, that was yi. So if I subtract yi, that's the error for the ith sample. So what can we do? Let's say, but I don't have to, I actually don't want to minimize the error at one place. I want to minimize error at all the pairs, so all i's. So maybe we try some ideas. Maybe first idea, let's say we want to try sum of errors. And do we see any issues with this? Yes. What is the issue? Let's say we have x1, y1 as 0 and 32, and x2, y2 then correspondingly we have from let's say minus 32 and 0, and that we can get, right? That's, let's say, assume that these are the two data points given. And we know that at 0 degree Celsius it is 32 degree Fahrenheit, and at minus 32 degree Fahrenheit it is 0 degree Celsius. So that's, let's say, it's given from our table. And let me say that I have A equal to 0 and B equal to 16, and if these are the only two data points, the error 1 is going to be, because this guy is always going to predict 16, correct? Because it is AX plus B, and since A is 0, it's all the Y's is equal to B. So it is going to predict 16. So in the first case, the error is 16 minus 32, which is minus 16. And in the second case, the error is 16 minus 0, which is 16. Now, if I do the sum of errors, minus 16 plus 16, that becomes 0. But is that pair good? Obviously not. So sum of errors doesn't work. So what we have to do? We have to avoid cancellations. So one of the way to avoid cancellation would be, if I square the errors and then sum them, then this also will become plus 256, this also will become plus 256, and we will avoid the problem of cancelling the errors. Okay. So now we turn our attention to just a simpler problem of inch to centimeter, where we just take y equal to ax, although the principle is same. So what we want to do is we use the square of the error and then sum them. So we want to find A, which will minimize the sum of square of errors. And that's why it is called, because it is minimized, it's least, and sum of squares, so it's called square. So this is called the least square solution. So what is the total error? Error is nothing but just half is something which you can put, you need not put, it's okay. So summed over all the examples, and then AXI minus YI whole square. And this is basically the error, because in this case I told you I am not considering any B. So Y equal to AX is the model. So this is the error. Now, if you look at this error, and suppose I have given you 100 data points versus next time I give you 300 data points, it becomes hard to compare the two situations, because the error will keep on growing also with the number of examples. So it's better to normalize and say, okay, what is the per example contribution of the error on the average? So to achieve that, I can just divide the whole thing by number of examples n. So basically we say this is the error. Now, what we can use calculus to solve it. And what do we want to do? We want to minimize E, right? This is the E we want to minimize with respect to A. So we set dA equal to 0, and we will not get into second derivative for now. And if you see it, you can see that you want to take dA. So if you look at this, then the derivative of this with respect to A, it's let's say assume this inner thing for a moment to be some variable z. So it is z square. So we know from calculus that it will become 2z dz, right? Dz dA. So dz dA is going to be simply xi, right? Because z is axi minus yi. So if you I'll leave the slides with you, but this is what the expression it is going to be coming out, right? Okay, and if you rearrange the terms, then basically you collect all the terms where a's were involved. So it will become a times 1 by n sigma I equal to 1 to n xi times xi, which is xi square. and minus 1 by n sigma yi times xi. Now, I did the calculation of, for our given table of data, this data, what you have been given here, I calculated sigma xi square and sigma yi xi, and then so this was the value divided by n. This was the value I got. So this led to a equal to 2.54, and which is great, because I know that if I want to convert inch to centimeter, I need to multiply by 2.54. But to begin with, here I didn't have that, but I really got it through some data points. Is it at this point? Are there any questions? Okay, let's continue. So now, what do we do for centigrade to Fahrenheit? Essentially the same thing. Only difference will be now it has AXI plus B minus YI square. Everything else is same, right? Now we have the error, which is function of two variables A and B, right? Okay. And what do we want to do? We want to minimize E, again the same thing, and we want to do dA equal to 0, and also dB equal to 0. Okay. We have also the second derivative condition to check, but I'm going to ignore for the time. Okay. Now, similar to what we did last time, if we calculate the derivatives, dA, this is what I'm going to end up with, right? The only difference will be here in the derivative, you have AXI minus YI, and in that case, you'll get AXI plus B minus YI. Rest all it will be same, because the derivative of this internal term with respect to A is still continue to be xi. So that's why the first term, if you see, is exactly the same, except that just this plus B has appeared here. And then if we collect the coefficient, the A coefficients of A and B, this is what it's the A part will be same. A times sigma 1 by n 1 over I equal to 1 to n xi times xi, which is xi square, and then you have B times 1 by n sigma I equal to 1 to n xi. This xi will appear there, and this term is again essentially the same as before. Now, additional thing we need to do now is we need to calculate dE by dB, and that's if you look at, so the first term is going to be again, so whatever we assume the internal thing to be z, that derivative is going to be still the same, 2z, and that's why the outside there was a 1 by 2, so the 2 got cancelled. And the derivative of internal term with respect to b is going to be simply 1, because b is just nothing around b, so that's going to be 1. So that's the derivative, that's it. So here there was a multiplication by xi, there will be a multiplication by 1, which is essentially the same, right? Now, if you do that, we have this result into A times sigma I equal to 1 to n times sigma xi, and plus B, because this B has no other term coming in, okay? And you have basically B summed n times and then get divided by n, so essentially it becomes just B. And then you have a third term, which is again similar to the last time, just here the multiplication by xi is not there. So this is the thing we get. Now here again, I have pre-calculated these numbers: 1 by n sigma xi, 1 by n sigma yi, 1 by n sigma yi xi, then this 1 by n sigma xi and 1 by n sigma xi square from this data, the centigrade to Fahrenheit. Okay. Now, moment I do that, then I think I just don't need. We don't need to go through the these calculations. But then we end up in having two equations in two unknowns, and solving that I get 1.8 and 32. So I get that y is equal to 1.8 times x plus 32, right? So that's the y is in Fahrenheit and x is in centigrade. So that we know that from our physics knowledge that's correct. But we got it exactly from our data points what we had, right? Okay. Now, sometimes you have multiple variables. I mean, here we had multiple variables in terms of multiple regression variables, but not multiple features. Now, I should have truly said from multiple variables, multiple features. So, suppose you have multiple features. Why do we have multiple features? Because let's say you want to have a house price to be, evaluated. Then you have, house size. You have number of bedrooms. You have garden area, etc., etc. There are so many parameters can be there, and I can't say add a simple y equal to ax plus b. In terms of company data, you have sales numbers, you have margin, you have debt, etc. So many things are there. So again, you cannot say that you will depend on only just one variable x. So many times you want to fit polynomials, then also you can treat x square, x cube, etc. as separate features. Okay. So again, just having x may not help. So in that case, we may want to have an equation like y equal to a1x, a0 plus a1x plus a2x square, so on and so forth, right? But function can still be linear in terms of features, because here, let's say the house size is feature x1, number of bedrooms is feature x2, garden area is feature x3, so on and so forth. Here also, let's say sales is x1, margin is x2, debt is x3. And when we are fitting polynomials, let's say x is x1, x squared, let's rename that as x2, x power 3, let's rename them as x3, because these are not variables. These are the data given to us. Because once x has been given, I can calculate x squared and x cubed. So my final function now can be y equal to some w0 plus w1 x1 plus w2 x2 and so on and so forth in terms of multiple variables or multiple features. And again, analysis very, very similar to what we have done here will apply, right? So the solution wise, what we have, it will be similar to centigrade to Fahrenheit, and this now starts getting really practical, and we can map many problems to this kind of situation. So we introduce, so in order to achieve, kind of a simple expression, we introduce an extra feature called x0 and we set it permanently to 1. Advantage of that, then I can write this as w0 x0 equal w0 x0, because x0 is 1. So in our earlier parlance, if you look at, we had ax plus b, now it will become ax plus b x0. So x0 is anyway set to 1 permanently. So our new set of x or features becomes x0, x1 up to xd. And then the parameters we want to learn are w0 to wd. The advantage of writing like this is using vector notation. I can write, if I say this is a vector w and this is a vector x, I can write y equal to fx as w transpose x. So that's the advantage. And then the error will be again the same thing. We evaluate w0 x0 plus up to w1 wd xd minus yi square. Now this again, if you look at in vector notation, I can write it as w transpose xi, right, minus this yi, and I can take norm of this. And I hope this is clear as how this comes. I mean, if somebody is finding it not obvious, one can write always as, if you write sigma xi square, then I can write that as x1 square plus x2 square, so on and so forth, up to xd square, and that becomes your x transpose x. So if you take this x and do x transpose x, you will get x0 square plus x1 square plus dot 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 plus xd square. So that's essentially the same thing I am trying to put here, right? Now, once you have this, then we need to take derivative with respect to w0, w1, w2, etc., and set it to 0. And then you will get, because they are taking so many derivatives, you are going to end up having, I'm sorry, there's a typo here. It should be d plus 1 equations, because we have gone from the x0 to xd. So there are d plus 1 parameters here. So you get, essentially, you get just like in the case of when we had a and b, we got two variables, two equations, and here we will get, d plus 1 simultaneous equations, and we can solve for these equations to get, the solution. Now, the solution approaches could be, one can be direct solution approach, where we solve using calculus formula and linear equation solver. But typically we end up using optimization methods, because we don't want to, compute such linear equation solutions, because that may also have its own issues. So in terms of speed, etc. So optimization, and also in terms of accuracy, depending on what methods you use. Also, there are other problems which we will probably not discuss in today's class at length, but some of the equations may be, something called ill-conditioned. The set of equations could be ill-conditioned, and we may not get a good solution using a linear equation solution. So we use optimization methods, and so what are the optimization method will do? We try to minimize this error and keep moving in W in order to keep minimizing the error, and we reach some final W. Okay. We will have a later talk on the optimization methods that will hint at what kind of optimization methods one can use. Okay. So now we try to get to the understanding of underfitting and overfitting. Okay. At this point, are there any questions done with the basic methods of linear regression? Okay. All right. So now let's try to understand a little bit about underfitting and overfitting. So let's say this green curve was some data of interest to me. Okay. And let's say this was, some kind of drawn from a voltage curve. Okay. So obviously you expect kind of a sinusoid. But we have to measure, let's say I measured the voltage at 10 points at 10 different times. Okay. And the blue dots are my measurements. Now, as you can see, the blue dots are not always on the green curve. And this is the reality. Why this is the reality? Because I may be using some voltmeter to measure these points, and the voltmeter may have its own inherent inaccuracies, etc. Right? So my observation in general might have errors. Okay? And we want to fit, let's say, a polynomial. So what we are going to try to do is we'll try to fit different order polynomials, and we will try to figure out which one is better. Right? Now, if I have a polynomial of quadratic, I know that given any 3 points, I can pass the quadratic without any error. So like that, since there are 10 points here, maybe it's good to, good to have a degree 9 polynomial, and that should have no errors because that will have capability to pass through all the 10 points, isn't it? Right? So, that's the thing one has to see that uh, that we need to make it uh, uh, the training error. Will refrain from using the word training error right now, but later on we'll see that this is called training error because that there are 10. These are the training examples, and we are measuring error over them. So, but is that degree 9 good? Let's see that. So, when I try to pass a first order polynomial, zeroth order polynomial, then what is the meaning of that? That means simply I can have y equal to b kind of situation, not even a. And then obviously I can only have a constant represented. So let's say this is the best fit constant after optimizing my errors, what we will be talking, right? And then if I want to fit a first order polynomial, then you have y equal to ax plus b, and then you can see that I can have a line with some slope, and you see how good it has fitted the data. M equal to 3, I see that there is a reasonable this red curve, that's a third order polynomial I try to fit. So the polynomial is like y equal to a0 plus a1x plus a2x squared plus a3x cubed. And then we see that there's a reasonable fit. Now, what you need to understand here is our aim ultimately. Okay, let me come back to that aim in a moment. But let's see what happens when we do ninth order polynomial. So, does anybody have any questions?
So how to fit the polynomial order? I mean, so when the curve is, we are obtaining a curve from the experiments. So which order it belongs to? How to fit it?
Yeah, just give me one moment. I'll tell you. Okay, so your question was mainly in terms of how do you choose what is the what order of polynomial to use? Is that correct? Was that the question?
Yes, sir.
Okay, so basically, see, we will get into that a little in a little while. Okay, first let's understand as to what happened when I tried different polynomials. So when I tried the zeroth order polynomial, then you see this is the diagram I got. The red line here. So that's a constant. That's all I can represent because y is simply equal to b. And I can find the best b to match. That's all I can do. Now, when I had first order polynomial, this is what I could get. This is the fitting was done using let's say some optimization method. Okay. Then when I did a third order polynomial, then I could get this red curve. when I go to ninth order, I was expecting that there will be no error on any of the blue points. That happened. See, this red curve now, the ninth order polynomial, passes through each of these blue points, right? But do you see this curve as useful or no? What do you see? Which curve do you think is better here?
X is equal to 1, M is equal to 3.
M equal to 3. Correct. Absolutely. That is better. But however, if you look at the training error or the error over all the examples, that is best in case of M equal to 9. Correct? Because it passes through all the blue points. So the error is 0. But our aim is not only to minimize the error over the blue points, but we want to understand how close we can come to this green curve. And these blue points, which are our observations, are only trying to represent this green curve. Okay? And that is the reason why here we were rejecting, because we knew this green curve, right? And this is nowhere close to this green curve. And the purpose of this getting this linear regression was to be able to predict the output at other points. So let's say now if I want to predict the output at this x, we are going to get a huge value, which is not correct. I should have got this value, but I am getting a huge value. At the same time, you want to predict at, let's say, this point, again, I'm getting a huge value compared to what I should have got, right? So this is not good, right? So let's understand as to what happened here. A little bit more details, right? So let's try to understand as to what happened. So this model was too simple. The M equal to 0 was too simple. It did not have enough variations to capture the variations in the data. So this now here, for example, for M equal to 0 case, if you add more data points, will it help? It won't. Why? Because essentially your model can only give a constant. Similarly, at M equal to 1, again, if you add more data points, it's not going to help. So the first two models, they are too simple a model and it does not learn my data well. Now, when I have too complex a model like this, that also does not learn data well. Why it does not learn data well? Because it does not learn the green curve well. It learns the blue points, but blue points are also having noise. So basically, it learns the noise. It ends up memorizing those 10 points. Okay? The first problem is called underfitting. And that's also known as high bias. So this model introduces a bias in what it can predict. And does not learn the training data itself. But one good thing about it is, if you take another set of 10 points from the same green curve, may not be the same 10 points, the result is going to be very, very similar to what you saw here. The curve is going to be very similar to this. So the thing is, model based on another data will be similar. So that's one thing which we can see. Now, what is the second problem? Second problem, which is here, this is called overfitting. Now, what's happening here? Here, it's a high variance. What is the meaning of high variance? We will probably see that in a little while. And then if I draw 10 different points, now from the same green curve, you have, say, another 10 points if I take, then this curve is going to look entirely different. Maybe this time, your curve with few points change, your curve instead of having a peak here, it may actually end up coming from this side. No, it may go hit the bottom and come back. So basically the curve itself, the model itself will perform model based on another data set will be very different. And another problem is it performs poorly on another data. So basically, if I want to predict at some point, predict at this point, so it performs very poorly on that data. And this problem is called overfitting. What do we want? We ideally want a model which learns the underlying data but does not learn the noise. And that, so how do we ensure that? How do we check that even? So for checking that, what we need to do is, once we have some set of examples, we need to keep some of them as called training examples and some of them as called, let's say, test examples. So let's say I have this 10 training examples and I have been given 3 more test examples. So what we are supposed to do is we train, or we find the regression model using those 10 points, and we want to check how they are performed on the remaining 3 test points, which we have not used in training. Okay, so then and whatever error we get in test data, we call it test error. Whatever we got error in training data, we get the training error. Now, if you see here, for m equal to 0, this is what we have done, the plotting for the example we shown there. For m equal to 0 and 1, even the training error is high. And test error is obviously high also. So, and that is reflected from the fact that this curve and this curve could not represent the data well enough, right? Now, you find that at m equal to 3, both are low, which remains kind of low till some 7, 8. And then at 9, you see that the training error has dropped to 0, but the test error is just shot up like anything, and which is not used. So anywhere in this region, if I choose my polynomial, I would have been good for the previous example we shown, right? So like that, one of you had asked question on how do I choose the polynomial. So you try different degree polynomials, try train and plot the training error and test error, and see where you are happy, right? So if and how do we predict whether it is underfitting, overfitting, or it is okay? So if both training error and test error are high, then that's underfitting. If training error is low but the test error is very high, that's overfitting. Okay, and otherwise in the middle zone it is kind of it's okay fitting. So instead of thinking of just a fixed polynomial, one must try different things before concluding which one I should use. Okay, so let's get into a little bit more insights into this and say, if it is underfitting, what should I do? Obviously, I have to make the model more complex. That means in our previous example, we could say we have to add more terms to the polynomial. So model should have more parameters. So I should use more features. Like instead of just x or just x, I should use maybe x squared, some powers of x. Okay. If it is overfitting, then model is already complex. More features will not help. I mean, if you make it more complex, it's going to make it worse. Like, for example, you have 9th order polynomial, you make it 12th order polynomial, that may not help. But other thing, what can help is if you get more data points, that will help. How that helps, let me just try to show you. So, let's say this is the kind of curve we got with data points being here, here, another data point was here, let's say, another data point was, let's say, here, another data point was here, another data point was, let's say, here. So we got 6 data, right? And let's say one more data point was here, and let's say one data point was at this place, right? Okay, fine. I mean, you just imagine 2 more data points somewhere. Okay. Now, let's say I start adding more data points. Let me use some other color to add data points. Let's say I start adding more data points. One here, one, let's say, here, one, let's say I got one more data point here, one, let's say I got here. What is the impact of this? Now if I try to fit the curve, as you can see, if it tries to fit the same curve, what's going to happen? The errors at these points is going to be big, right? So what it will do is, it will probably have some error at these points, but try to accommodate, little bit better, right? So you can see that if you add number of if you increase the number of data points, maybe even with the complex model, you can fit a better model. So that's another way of tackling overfitting. So one other way to tackle overfitting could be to reduce the complexity of the model, and another way could be getting more data points. One has to be very, very careful in this, in terms of many times what may happen is, if we are having a machine learning kind of problem and we don't get good enough accuracy, then we tend to conclude that we need more data. However, without realizing whether we were in underfitting or overfitting, that can be a very dangerous exercise, because if we are underfitting, then no matter how much amount of data you get is never going to help. So first thing is to conclude whether we are underfitting or overfitting. If we are overfitting, maybe more data will help, right? So that's what we need to keep in mind. Okay. So another way of there are more ways in terms of regression. There are other ways of, instead of just getting more data, sometimes maybe you have got some data and you can't get any more, the source is not available to you. Then there are two kind of methods which are used. One is called subset selection, and other one is called shrinkage method. So let's understand what these methods are. So what we do in a subset selection is, we retain a subset of variables. Let's say some k variables only, where we had, let's say we tried to fit a d order polynomial, then we had d plus 1 variables, right? Like w0 to wd. Now what we do is, the general idea is, we select some k of them and use this square method to solve. It looks very simple to describe in 2 lines, but it is not possible to try, because trying all subsets may be a really hard thing to do. How many totally, you have to see how many such subsets can be formed. I mean, you can have exponential number of such subsets which can be formed. For example, if I want to choose one variable, then there are d plus 1 chances, right? I could have chosen w0, I could have chosen w1, I could have chosen w2, so on and so forth. So d plus 1. If I want to choose, let's say, 2 variables, I have roughly d square by t d square by 2 possibilities, right? Roughly. Actually it's going to be, d choose 2. So it's a combination thing, right? In how many ways you can choose 2 out of d elements. And the choice could have been w0, w1, w1, w5, w2, w3, so on and so forth, right? So it's, in general, if you look at, it's not a good idea to look at that, right? So there are some heuristic methods which you use for subset selection. So there is one method which is called forward stepwise selection. What you do in that is, you start with a constant function, okay, and sequentially you add the parameters which improves the fit. So let's say you already start, you ran with, let's say, only one parameter, all d of them, and then chose the first parameter which gave you the best error. Then you keep that error as old error. Now out of the remaining d minus 1 parameters, you choose one at a time So let's say the parameter x w3 has already been chosen. Now you find the error, new errors. If you have to choose w3 and w0, if you have to choose w3 and w1, if you have to choose w3 and w2, if you have to choose w3 and w4, so on and so forth. So there are d minus 1 pairs like that. Now, out of these pairs, you calculate the gain f in terms of old error minus new error divided by new error. So that's the percentage gain, and you kind of weight it in terms of the number of parameters k you have right now by dividing by n minus k minus 2. Okay. Now, whichever parameter has given this number f as maximum, that's the parameter you can choose to improve your fit, and that way you can keep adding one parameter at a time and get the get your final the final set of parameters. Now, at some point, if you find that adding any parameter is not improving the error significantly, maybe that is the time to stop. Even if you decided to go with some k, even if there's some lower number, lower than k, if the additional parameter is not yielding any good f, then maybe you stop at that point itself, and that's the model you choose and say, this is what I'm going to do. Is that clear? Okay. So then the another way is backward step size selection. So this is exactly, you can say it's very similar to the previous one, forward step size selection. But the only difference is there I started with one parameter and kept on adding one at a time. Here I start with all the parameters and define a similar f and use that to keep on dropping the parameters sequentially. So at the first level, I'll drop the parameter which did not decrease my performance too much. So I suppose, let's say I had certain error. Let's say I had error of 0.01, and by removing parameter w3, that 0.01 changed by, let's say, then I can say, okay, dropping that w3 was good for me, and I don't need that. So like that, you sequentially keep dropping one at a time till you come to a place where either you see that the any more parameter dropping will significantly increase the error, or you have reached a pre-decided number of parameters you wanted to keep if you have some other concept. Right. So this is the subset selection method. Other method is called shrinkage method. So shrinkage method, what it does is, it tries to put some kind of restriction on the value of these coefficients. So each of these coefficient W1, W2, etc., it tries to put some kind of constraint on the coefficient so that the coefficients can't grow too much. And if the coefficients can't grow too much, then the curve becomes a little bit better behaved. Okay, so the difference between the one major difference between the subset selection and shrinkage method is subset selection was a discrete process. Say one variable, either you drop it or you keep. You can't keep it partially, or you can't do anything about it, right? You either you keep it or you don't keep it. So that's a discrete process, and sometimes the prediction error may be high because of that. The shrinkage method is not a discrete method. It tries to keep all the coefficients but tries to shrink them. Now, so one of the idea is called ridge regression. And what does the ridge regression do? Ridge regression is basically, it penalizes high value of coefficients by adding the sum of coefficients square of sum of coefficients to the cost function or to the error function. So obviously, if this number goes high, then my error or whatever my thing I am trying to optimize, that will keep on going higher. How do I control how much say I want this to have? By a regularization parameter called lambda. Higher the lambda, it will tend to shrink the coefficients more. And if you keep lambda very, very high, almost each of the wi's are going to become 0. So high lambda would go towards underfitting, and some very lambda 0 sometime may be overfitting, and some small value of lambda may lead to good fit. So that's penalty function approach, and this is called ridge regression. There is another approach which is called lasso, and only difference is between the two approaches. Basically, here you are adding sum of squares of error. There you are adding just the sum of absolute values of the errors. Okay, so that's the only difference. This norm W is basically this is I should have probably written more clearly here. This is not the square and taken square root, but so this is basically instead of adding the square, you are just adding the norm of the okay, and the effect of that is going to be that this is equivalent to that minimizing this function subject to some this norm being less than equal to some number s. So this actually results in many of the coefficients going to 0. Okay. Now, why that happens, we'll just try to understand through a diagram. Okay. So these are called these are the function contours. Like my this is the contours means this is the so this is my function. The first part, forget the second part right now. The first part, now with different values of W, how the the function value is varying, right? That is what we need to see. So a constant function contour will be set of all W's having a constant value of that. So for example, if you look at this outer ellipse, then what's happening is that this has a certain error value. Okay, so all these points on this curve have the same error value. Similarly, the lower ellipse you see that has another constant error value. Let's say this is the error 0.5, this is error 0.2, this is error 0.1, so on, and this is finally error 0. Okay, so they are the center. So that's my error curve, the error contour. Okay, and then as I told you, if you look at norm of W equal to some less than equal to some number, then this is going to be the plot. Okay, if you are just doing the absolute value of the error, this is going to be the plot, right? Of some this is the shape of the plot. Okay, so if you want to increase this as much as when you touch this error surface, you stop there. Okay, now this is the contour. This is same contour, and this is the sum of squares. So when you say, for example, when you say W1 square plus W2 square less than equal to some number, then you know that is going to be a spherical kind of surface. Now, what you are trying to do in lasso is trying to expand this as much as you can to touch this error surface. And same thing you are trying to do in this. So if you look at geometrically, it's obvious that this you can try it out also drawing in a sheet of paper, and you will see that this tends to meet these error curves on some axis. say here it is meeting on the second axis, right? But when you have this kind of round surface, then that tends to meet anywhere, right? So if it meets anywhere, then what happens is none of the parameter, none of the coefficient is zero. See, and here, if it meets on some of the axes, because the way it is pointed towards axis, it tends to meet on some of the axes. And when it meets on some axis, then you see that other coefficients have become zero. So that's the reason why lasso results in many coefficients going to zero, and ridge doesn't result into many coefficients going to zero. Although this does put a constraint, any of both of them put a constraint on the amount of value a coefficient can have. So many situations lasso is preferable, where if lots of coefficients go out to zero, let's say you have a decision making problem and you fit it as a linear regression thing using lasso, and many of the coefficients have gone to zero, then whichever coefficients have not gone to zero, you know that you have got the important features. So less important features it tends to ignore. So that's the that's the way you another way you handle overfitting problems. Okay. Now, one of the very important thing is to understand this bias mean variance decomposition of the linear regression problem. So, and which will be useful in other situations also. So, let us assume that I have true function f and I have measurements y. So what does it have? It has true function as well as some noise or error in measurement. So what I have is actually y equal to fx plus epsilon, and I have been given several measurements of this, and we want to fit some curve h of the form hx equal to whatever w transpose x or w dot x, the dot is same as transpose, to minimize this error as we have talked before, right? That's our aim. Now, what? So let's say this is these are the points here. You can see in gray here. These are the points, and I have tried to fit some curves through this, right? Some estimated. This is the blue line is my estimated edge. Now, so if I get different set of data points from the same curve, same red curve, I'm going to get different edge based on different data sets, right? So now what should I do? What I'm trying to do? I don't know what data I'm going to get. So there's no point trying to look at properties of this H itself. I want to look at the properties of this group of H as I'm going to get as based on different data sets, right? So then, so what are we interested in? We are interested in given X star, predict Y star. And we want to understand the error. Now, characterizing with respect to single H is not so important, because next time I repeat the whole process, I'm not sure whether I'm going to end up with the same data set or not. So we want to understand overall how well this group of H is doing, right? So we want to understand goodness of on single H or multiple H. We want to understand not goodness of a single H, but the whole process or method which you are following, and not on one set of data points. So we have to define error with multiple scenarios. So we have to somehow define error for this scenario to understand how well we can understand that, right? And so what we do, we can always use expectation, right? So so basically we want to reduce the expected error, not just this error of hx star minus y star, but the expected error of hx star minus y star square, right? So we will use a simple notation where we'll say x bar as expectation of x, which is nothing but the mean, and expectation of x minus x bar square, which is the variance. We call it. Then that will be nothing but ex. That if you look at expand it further, you can prove that this is equal to ex square minus x bar square, and that's which is variance of x. And in other words, if we use that, then what we have is expectation of x square is equal to nothing but variance of x plus mean of x square. Okay, so this is just an expression I'm going to use it. Okay, So, so what we wanted to do was we wanted to minimize, we wanted to look at the property of this expectation of hx square, hx star minus y star square. So we just expand it. Just the inner term, we just expanded. It just looks too much of math, but it is not complicated at all. So this is what we get, right? Now we know that expectation can be moved inside. So we move the expectation inside. So this has become E of hx star whole square minus 2 times E of hx star times E of y star plus E of y star square. Okay. Now, that if you now, I'm not going to manipulate this here, but this expression, if you use this expression here, E of x square is var of x plus variance of x plus mean of x square. If you use that, then expectation of hx star can be written as variance of hx star plus mean of hx star square. So that's basically that's what I'm doing here. And expectation of hx star is simply nothing but the mean of x star, hx star, and ey star. What is the expectation of y star? So let's look at that. From this expression, you can get it. So I put expectation on both sides. So expectation of fx will be so let's say y star is equal to fx star plus some epsilon. So expectation of y star is nothing but expectation of fx star plus expectation of noise, which is going to be 0 if I assume 0 mean noise. So that's how you get expectation of y star as fx star. Okay, and this one is again very similar to what we used here. Okay, so once you do that, then and you cancel all the terms, what you're left with is variance of hx star plus variance of y star plus h bar x star minus fx star. Now you look at this term. This is a variance of my estimator h, right? And look at the third term. This is the mean of the estimators, and this is the value I should have got. So this is the, you can say, the bias which the family of estimators have introduced. So this is the third term is just nothing but bias square, and the second term variance of y star is nothing but the noise term. So whatever is the noise variance of epsilon, that is a noise, right? So if you look at my final error, these are the three components of error, and since all of them are positive, there is something which I need to understand here as what is in my control, what is not in my control. If I look at the noise, that may not be so much in control because that is something which is inherent to the way I am measuring things. So unless I improve my measuring equipments or the way I collect data, I reduce those errors, I may not be able to do much in that. So that's the third term, which is not in our control of linear regression. It may be in control of data collection, but not in terms of linear regression. So in linear regression, we are left with these two, and it is often found that the variance, if you want to reduce, you can do that by trading by having a little bit of bias. Okay, and so if you introduce complete bias in terms of making h of x star itself as a, let's say, a mean as a constant or a zero, then you will find that the variance so the bias will be very high, but variance will become zero. Well, each of the estimator will be exactly a constant, right? So that if I choose h of x star equal to some constant c, then that's the situation I get into. Very high bias, but zero variance. Similarly, the overfitting case you have seen, that kind of situation, I can have zero bias, but I can have a very high degree of variance. So somehow, if you look at, I leave it as an exercise to see for yourself or do some research on it, find out. I know that if you introduce lasso or this kind of techniques where you have got this lambda as a regularization parameter, what the effect lambda will have is it will introduce a little bit of bias, but it will control the variance. Okay, so that's why often you hear the term, bias variance trade-off. So the trade-off is in terms of introducing little bias to control the variance large. So that's what I wanted to cover. Last 10-12 minutes are there. I wanted to keep for question answers. Thank you very much. Any questions? Yeah, any questions? Okay, the second question I see how lambda impacts the high value coefficients. Okay, we let's go back to this. Okay, now what's going to happen is, suppose I choose lambda equal to 0.1. Okay, now whatever error calculation I am doing on that, I'm adding point, and let's say there was only one coefficient W1. Okay, just to simplify, just to understand the. So what I have is, let's say lambda is 0.2. So this is, the whole thing is 0.1. So I have added 0.1 W1 square to the whole error term. Now, if W1 becomes too high, this error term will become high, right? So this, once I have some positive lambda, and the only way to decrease this overall error would be to decrease the value of W1 square, and in terms, in other terms, that will shrink the value of W1. Now, supposingly you increase the lambda further, make lambda equal to, let's say, 2 now from 0.2. So now we are simply adding W1 square itself to the error. Let's say the error was 10, and W1, if W1 was 10, then you are adding 100 to it and making it 110. So you will actually, if supposingly at W1 equal to 5, the error was only, error was actually the first part of the error, instead of 10, even if it became 12, the sum is going to be 12 plus 25, which is 37, which is far better than, the at 10, W1 equal to 10, the error would have been 110, right? So that way, lambda plays a role in terms of higher the lambda, lesser the value, the more the parameter values will be shrunk. Any other questions? So if there are no questions, I'm not able to see all the chats. If there are questions, please speak up and ask, because I'm not able to see all the chats. Speak up, ask some question. Yeah. Yes.
Bias in this, it was not.
Yes, sir. Question was there, do you have any technique to fit a model for a set of given data? So as I told you, either you know from the domain of the data what kind of model can fit, or you should view the data to figure out what type of model can fit. Somebody wanted me to explain the plot of training and testing data once more. Okay, so I'll just go back to that and explain that. Okay, and wanted to know why lasso is preferred over ridge. Okay. Okay, fine. I'll try to answer these couple of questions. I think that's all I'll have time for. So one of the question was explaining this. So what we are doing is here, let's say I have 10 training points, which I have used to, used to calculate my the regression function. Okay, so let's say these 10 blue points are the ones which are my data points. Based on them, I have calculated the the curve. Now let us assume that I have 3 more points which are test points. So let's say this is my one test point, this is my another test point, and this is my third test point. I'll exactly put them in the same place here. This is my first test point. This is my second test point, and somewhere here is my third test point. Okay, and similarly assume that I put it on this also. Okay, this is the first test point. I'm sorry, I'm not able to put it the exact same place, but I think you understand, right? This is my second test point, and this somewhere here is my third test point. And I'm going to skip this first one. I'm not going to. So now you first, what is the training error? Your training error is error of between this red curve and these blue dots, right? And I calculate that for these training points for all m equal to 0, m equal to 1, 3, 10, etc. And this is what I plotted here, right? This is what I plotted here in the blue curve. This is the training error. Now, note that for this m equal to 9, this curve passed through each of these blue points. That means there was no training error. Okay. Now, how do I calculate test error? I calculate this same kind of error, but for these green points which I have selected now, which are the test points which are not used for deriving the curve. So here I have, this is the error I have here, this is the error I have here, this is the error I have here. I take the square, sum them up, and divide by 3, just so that because there are 3 examples, and that's how I get the test error. So similarly, I get the test error here, right? From the red curve, I get the test error, right? And similarly, if you look at here, the test error, right? So you can clearly see that in the overfitting case, the test error is really high. So what we see here is we plot the test error also for different polynomials, and then we see the what we observed there also for m equal to 9, the training error is 0, but the test error is very high, right? So that's the thing, right? And okay, now so one more question was on why we prefer lasso to ridge. It's not that always we prefer, but sometimes it is in a management decision kind of situation. Let us say you have 8 parameters which can impact your organization. Okay, and so what is the impact of these parameters having on your, let's say, your profitability? So these are the, let's say, the coefficients. Now you possibly cannot address all the 8. And or possibly it becomes too complex to even understand how those 8 are playing. Okay. Now instead of that, if you use lasso, then what is going to happen is out of 8 parameters, some of them may go to 0. So now you're left with only 3 parameters, let's say, which are significantly impacting my profit. So now I need to only address those 3 as opposed to address all 8, right? And that's why lasso is actually preferred, right? In those situations where we want to really understand situations. And many of the decision theory stuff, when you have to explain your decision, lesser the variables, better it is easier it is to explain, right? So those are the situations in which you tend to prefer lasso. Any other? Okay. Shall we close it?
Sir, there is a one request.
Yeah.
Sir, can you share your PPT? with the-
Yes, I have one more at 11:30, right? I'll send you both.
Okay. Thank you.
After that talk, I'll actually go to, you give me one email ID, I'll mail it to that, no problem. Or I'll mail it to Professor Nagarvishnu.
Thank you, sir.
So can we close now? Thank you everyone, and see you in half an hour. Thank you, bye.